Hi everyone, this is going to be a video about Fischer projections and stereochemistry. And before we get started, I just wanted to let people know that I did create and I am offering under the free resources section of my website a complimentary guide for free that goes along with this lecture. So if you would like a copy of everything we're going to talk about, and you also want additional practice problems in comparison to what you see in the video along with an answer key, go on over to chemcomplete.com and under free resources, go ahead and grab your guide. Now, on to the lecture. Hi there, everybody. I wanted to do a lesson here on determining R and S for Fischer projections. So we're talking about stereochemical configuration when we get to Fischer projections, because I find a lot of students already have trouble determining R and S when they're dealing with three-dimensional projections, so your regular carbon backbone chain with the wedges and dashes. But then when we get to Fischer projections, it becomes even more confusing because you just start learning the three-dimensional rules and then we make it flat and it goes two-dimensional. And then students are wondering, where do I orient the lowest group and all that kind of stuff. So if you're not familiar with assigning R and S and stereochemical techniques, this is not exactly going to go through all of the Ingold rules and things of that nature. We're just going to be looking at it specifically related to Fischer projections here. So a Fischer projection is going to take a carbon backbone that is three-dimensional, and you're almost viewing it as though you were hovering right above the carbon backbone, and you're going to push it flat onto a two-dimensional plane. So think of it almost like a sheet of paper that you're pushing this down on. So if we were to take a look at that, you've got a pushing down flat of this three-dimensional structure, it moves over into the two-dimensional realm. All right, so this is what everybody is used to seeing when we have Fischer projections. And especially when we get to like carbohydrate chemistry and sometimes amino acid chemistry, but really carbohydrate chemistry, we start using these. And you'll see the Fischer projections, right, that have multiple. So you'll have like OHH and then OHH. And you've got multiple rounds of this hydroxyl hydrogen going on. And then usually you'll have some sort of like an alcohol and either a ketone or an aldehyde at the top of the chain. And so this is very relevant to biochemistry when we start looking at those types of structures and molecules. Now, the Fischer projection, when it is viewed flat, and again, I'm keeping the transition up here, you can see that the left and right were facing above the plane. So take a look at this right here. Okay, A and B were coming above. If you imagine, here's the plane that I'm drawing right here. Okay, A and B were coming above the plane, and so that's where you find the left and the right. And then C and D were going, and the up and down were facing below the plane. So you can see the C and D that were below the plane. They are now the up and the down. All right, and the important note here is that the top position was facing out and away. So we're talking about D here. So when I get to D, D is found in the up position here. And that can make it easier for many people because when we do the R and S assignment for stereochemistry, we always attempt to get the lowest priority group, rank 4, to be facing away from us. And so if we keep in mind that this should be where rank 4 is going to be put, that will help us in determining our R and S. Now, that doesn't mean that whatever is there is always rank 4. We would have to manipulate and rotate the molecule in order to get it to that point. So we want the top position that was facing out and away to be where the lowest ranked priority group is going to be for R and S. All right, now, how can we deal with projections? You can do one of two things in order to manipulate projections. The first thing that we can do is rotate projections 180 degrees. You cannot turn them 90 degrees and you cannot turn them 3/4 of the way. So you can't do a 270 degree turn. You have to turn it 180 degrees. The other way that you can manipulate sort of these types of 90 degree and 270 degree turns is that you can hold one of the four groups constant, and then you are allowed to freely turn clockwise or counterclockwise the other three remaining groups. So let's take a look at one of the simplest structures we have as far as sugars are concerned, and that's glyceraldehyde. So for the glyceraldehyde example, the first example here would be where we have moved this 180 degrees. So that was the first of the two acceptable methods for turning a molecule. So if you found it helpful in a given situation, you would be allowed to take this structure, rotate it 180 degrees. What was on the left is now on the right. What was on the right is now on the left, and then what was up is now down, and what was down was now up. So you're really just completely turning it around. Now remember, we only truly change stereochemistry if we're taking two of the groups and removing them while keeping two of the others constant. So just rotating it like this did not turn it into an enantiomer or anything like that. This is still the same compound. We haven't changed any of the bond alignment. And that's one of the reasons you're allowed to do this, is because you're taking the same molecule and you're simply rotating it. You're not actually changing the stereochemistry of that molecule. However, if this helps you in determining R and S or some other way you want to view the molecule, then you're allowed to do that. So the other thing that we are allowed to do is you can hold one of the groups. So in this case, I have a hold on the aldehyde group. And so what I'm going to do is I'm going to hold the aldehyde group exactly where it is, above there, and then I'm allowed to rotate the other three in a clockwise or counterclockwise method. So in this case, I'm going clockwise. That means the H is going to pass over what I'm holding constant, so it's not going to go up there, and it'll come over to the right-hand side. The hydroxyl is going to move down, and then the alcohol is going to move up and to the left. And you can see that result right here. Here's the hydrogen, here's the hydroxyl, and here's the alcohol. But I kept my hold on this aldehyde group. And so this is an acceptable method of rotation. Usually, most students find this second method useful because you can really hold any of the four constant that you want. And that way you are able to get your lowest priority group up to the top. So let's practice this for just a moment and determine, do we have R or S in the following situations? So what I would suggest that you do here is pause the video and try this out and see if you can come up with the answers. Then unpause it and see the walkthrough. So I've actually got 4 of these here. I'm going to bring the other 2 up. So take a look at these and see if you can solve them. All right. Now what I'm going to do is I'm going to go ahead and move forward with this. So hopefully you did pause the video and you had a chance to work this out. So what I would do in each of these cases, the first one, I'm going to hold my methyl group. So I'm going to put a hold on this, and I'm going to rotate these counterclockwise in order to get the H to this upper position. Because remember, I'm really trying to get this to position 4, whatever position 4 might be up here, and hydrogen is the lowest ranking when we deal with this. So the way that I would restructure this Fischer projection for ranking is that I would now have the hydrogen on top. I moved counterclockwise by 1 position. So my carboxylic acid would now be hanging out over to the left. On the right, I would find the amine. And then down below, I held the methyl constant. So if I were to do a ranking of this, it would be 1, 2, 3. And if I follow this, this goes counterclockwise, so this would be ranked as S. Okay, now following a similar principle here, I'm going to go ahead and I'm going to hold the methyl constant due to the fact that I want that hydrogen up in the top position. This time I'm going to move it clockwise, so these will all rotate like this. And the Fischer projection that I'm going to end up with, we'll keep the methyl the same. And then we will have the aldehyde portionality over on the right, and over, well, we'll have the hydrogen up top, and then over on the left will be the hydroxyl group. So if I were to rank this, this would be 1, 2, 3. 1 to 2, 2 to 3. So I'm going clockwise. This one would be ranked as R. This one was S. So continuing forward, hopefully you're getting sort of in the groove and you're starting to recognize what we're going to do here. Again, I'm going to hold the bottom constant, which is a common theme as I'm attempting to get this hydrogen up into the top position. So as I do this, I could go ahead and I could rotate this clockwise. And if I do that, I'm going to end up with a Fischer projection that keeps the ethyl at the bottom. And then I would have the methyl group over on the right. I would have my hydrogen up top, and I would now have my aldehyde over on the left. And the ranking for this one would be 1 for the aldehyde, because we don't have an oxygen or nitrogen directly attached now. And number 2 would be the ethyl group, because it's larger. Number 3 would be the methyl group. If I'm going 1, 2, 3, that's counterclockwise. So this would be S. And now for the last one. For this last example over here, I'm going to again hold constant at the bottom. And when I move over here, I would take a look at this and I would say, all right, I want to move these counterclockwise so that the hydrogen is going to be at the top. And in order to draw this, I would hold the amine constant at the bottom. I would then move the hydrogen up top. The hydroxyl would be coming over to the right, and then the aldehyde would be over to the left. And so ranking this, I would have 1 for the hydroxyl, 2 for the aldehyde, 3 for the amine. It would be 1, 2, 3, and I yet again have S. So hopefully you found this useful in how to solve for and predict R or S chirality when we're talking about Fischer projections. Remember to subscribe for any new video content that's coming out. We're trying to push out regular videos every week now. And if you leave a comment, I will try to get back to you. Drop a like if you found that this was a helpful lesson. And we, as I mentioned at the beginning of the video, have a free guide or portion to our website that allows you to pick up individualized items that go into more detail and practice of some of the things we cover on the channel here. And I do have a free guide to the Fischer projections. So if you head over there, you are welcome to grab a hold of that, and you can browse around and see what else we offer over there to support the channel, like our larger guides and our services for one-on-one mentoring. So thank you very much for learning with us, and we will see you guys next time.